So a very good afternoon to everyone. So I'm Rohit Gehlot and I will be taking the week 8 doubt session for the material characterization course. So in the last week we discussed about the basics of XRD, like the how the X-rays are generated, and then the different filters, about different filters, and how uh, different sources, and also we end up at the scattering of the X-rays. So before starting, firstly, the major application of the XRD can be classified into five things. First one is the crystal structure determination. Second is the lattice parameter determination. Third one is the calculation of the phase fraction. Fourth one is the residual stresses. Fifth one is the crystallographic texture or preferred orientation. So these five applications are majorly used for the XRD. And then here also the XRD of some specimens are presented. There is a different XRDs. So before starting the lecture, firstly, let's understand what is the diffraction. So a diffracted beam may be defined as a beam composed of a large number of scattered rays mutually reinforcing each other. As seen in the figure, like there is a particle and there is a crystal. These are the X-rays. So they interacted with the single particle and here with the crystal. And then after the interaction, there are a large number of scattered rays which are reinforcing each other generated. Then this is called the diffraction. And then if we understand the origin of the intensity versus 2 theta plot, which is the shown in this first slide of the today's I versus 2 theta. So this is your specimen sample, and this is the incident beam. And then some rays are like completely transmitted. However, some are the diffracted beams, diffracted beam 1 and 2, and then the plot of the intensity versus 2 theta is plotted to obtain the necessary I versus 2 theta plot. If we come to understand the interaction between the interaction of XRD with different if the XRD is interacting with your crystal, then this systematic peaks are observed. However, if it interacts with an amorphous solid or liquid, then there is a single peak is observed. However, in case of monoatomic gas, there is no single peak is observed. Okay. And then if we talk about the diffraction under non-ideal condition and ideal condition. So firstly, for the ideal condition of XRD, it states that your crystal should be perfect. Then the incident beam should be composed of a perfectly parallel rays, and then they are strictly monochromatic radiation. However, these conditions never actually exist because the incident beam in the most powder diffractometer is divergent, and the characteristics lines from the X-ray tubes have finite spectral width. Okay, so in the ideal condition, most cases don't exist. And then if you talk about the destructive interference is produced in all directions except those of the diffracted beams must be understood, because it is a fundamental to the theory of diffraction, and therefore how destructive interference is produced is important. Okay, as it will lead to the method for estimating the size of very small crystals. And if we talk about the condition for the reinforcement, which means that the waves involved must differ in some path length, there should be a difference in the path length, which is in phases, by exactly an integral number of the wavelengths for conducting the constructive and destructive interference. As seen in this figure, like there are rays 2 and 3. These two rays do not annual each other at wavefront BB'. This is your wavefront BB', and simply unite to form a beam of smaller amplitude. Okay, as seen that the resultant beam's amplitude is slightly reduced than the previous one. So because of particularly the difference in their path lengths. Now suppose that the angle theta in following figure is such that the path difference for the ray scattered by first and the second planes A and B is only a quarter wavelength. Then what will be the resultant amplitude? As seen here, there are like these two planes. Then these are the rays scattered. This is the plane wavefront coming, and then this is the after diffracting this going on. So what will be the resultant amplitude of these incident waves after diffracting? So they will form a beam of the smaller amplitude. So if anyone can tell me the reason why it will be happening. So because as seen in the figure, like here, the reason is the same as the before, as the amplitude, because the two rays are completely in phase. However, the as seen here, but the resultant amplitude will decrease. Then the question comes, how the destructive interference take place, and then for this, how the destructive interference takes place. So the answer lies in the contribution from the planes deeper in the crystal. So under the assumed condition, the quarter wavelength, the rays scattered by the second and the third planes would also be a quarter wavelength out of the phase. Okay, so that is, the rays scattered by the first and the third planes are exactly half a wavelength out of phase and would completely cancel each other. So we can say that when the path difference is exactly one half of your wavelength, then they cancel out each other. Okay, because of slightly so we in the theory, in the lectures we discussed that the destructive interference is just as much a consequence of the periodicity of the atom's arrangement as it is for the constructive interference. It follows that there is a connection between the amount of out of phaseness that can be tolerated and the size of the crystal. Okay, and then the crystal is very small, and then the result is that the very small crystals cause broadening of the diffracted beam. That is the diffraction at angles near or but equal to the exact Bragg angle. Okay. So now let's take an example. So if the path difference between the rays scattered by the first two planes differ only slightly from an integral number of wavelengths, then what will happen? Then the plane scattering a ray exactly out of the phase with the rays from the first plane will lie deep within the crystal. Okay, and then if the crystal is so small that this plane does not exist, then the complete cancellation of all the scattered rays will not result. So it follows that there is a connection between the amount of out of phaseness and that can be tolerated and the size of the crystal. So let's take another example. So as seen here, at a diffracted angle 2 theta, seen here diffracted 2 theta b, a dash, d dash and m dash. These are the a dash, d dash and m dash are completely in phase. So these are completely in phase, and then they unite to form a diffracted beam of maximum amplitude. Okay, so the ray B, this is the ray B, makes a slightly larger angle than your completely Bragg angle theta B. It is making an angle of theta 1, which is greater than theta B, slightly greater than theta B from the mth plane. From the mth plane, below the surface, it is m plus 1 wavelength out of the phase with B dash. Okay, the ray from the surface plane. This means that the midway in the crystal, there is a plane scattering a ray which is one half, actually an integer plus one half wavelength out of the phase with ray B dash from the surface plane. So these rays cancel one another, and so do the other rays from the similar pairs of the planes throughout the crystal. The net effect being that the rays scattered by the top half of the crystal and annul those scattered by the bottom half. So the intensity of the beam diffracted at an angle 2 theta is therefore 0. Okay. Now let's take another example. So the intensity is also 0 at an angle 2 theta 2, where theta 2 is such that your ray enters from the mth plane below the surface is m minus 1 wavelengths out of the phase, with ray c dash from the surface plane. So it follows that the diffracted intensity at angle near 2 theta b but not greater than 2 theta 1 or less than 2 theta 2 is not 0 but has a value intermediate between 0 and maximum intensity of the beam diffracted at an angle of 2 theta b. Okay, so as seen here, so this is your thickness of the material. T is m times your d, interplanar distance, and this is the incident B, the complete Bragg angle, and these are the other incident beam B, C, slightly more or less than your Bragg's angle, and then these are the scattered beams. Okay, so your intensity will also be 0 at an angle of 2 theta 2. This 2 theta 2 is slightly lesser than your Bragg's angle, and then if similarly for the m minus n minus n times wavelength out of your phase with ray c dash. This is your ray c dash from the surface plane. So here also the resultant intensity will be 0. So slightly at higher theta 1 and at lower theta 2, the resultant intensity at some particular distance, it will be 0. Now if you talk about the measure of your peak width, that is full width half maximum. So this is your full width half maximum. Okay. So these two shows that your so here we talk about the integrated intensity, which is the area of your this one. So here this is your half times, this is the average of half I maximum, and top one is the I max, and then this lies between your the angle is 2 theta 1. 2 theta 1 and 2 theta 2, and then this is the Bragg's angle at 2 theta b. Okay, so effect of your fine crystallite size on your diffraction curves. Okay, so if you talk about the if you take the difference between these two, then it will be half times of 2 theta 1 minus 2 theta 2, and it will be theta 1 minus theta 2. Then the path difference equation for these two angles are 2t sine theta 1 will be m plus 1 lambda, 2t sine theta 2 will be m minus 1 lambda, and then by subtracting we find that t sine theta 1 minus sine theta 2 will be equal to lambda, and then if we put the formula then for sine c minus sine d, then we can write it as 2t cos theta 1 plus theta 2 by 2, and sine theta 1 minus theta 2 by 2, it will be equal to lambda. And then solving this we will get the theta 1 plus theta 2 will be 2 theta b. So and then for lower angles it can be taken as theta 1 minus theta 2 by 2. Okay, so it can be taken as theta 1 minus theta 2 by 2. So we equate it as 2t theta 1 minus theta 2 by 2 cos theta b is equal to lambda, and then from here we get the relation between your or we call it as a Serrer formula. So a more exact treatment of the problem uses. So t can be written as 0.9 lambda by b cos theta b. Okay, so let's take an example. So what is the order of magnitude of this effect? So suppose your lambda is 1.5 angstrom and d is 1 angstrom, and then the theta is your theta is 49 degree. Then for a crystal 1 mm in diameter, the breadth b due to the small crystal effect alone would be about 2 times 10 to the power minus 7 radians, or too small to be observable. So such a crystal would contain some 10 to the power 7 parallel lattice planes of spacing assumed above. However, if the crystals were only 500 angstrom thick, it would contain only 500 planes, and then the diffraction curve would be relatively broad, namely about 4 into 10 to the power minus 3 radians, okay, which is around 0.2 degree. So for non-parallel and non-monochromatic incident rays, if you talk about, so these are the perfectly parallel beams and has never been produced in the laboratory, as any actual beam of X-ray contains divergent and convergent rays as well as parallel rays, and also the any real beam is never strictly monochromatic. So then your copper K alpha line itself has a width of around 0.001 angstrom. This narrow range of wavelength in the nominally monochromatic beam is further cause of the line broadening, which is a measure of which is a measurable diffraction at angle close but not equal to 2 theta. Okay, since for each value of lambda there is a corresponding value of theta, for example this. Okay, and now we also discussed in the class about the different factors which affect the relative intensity of the Bragg reflection. So these are the structure factor, polarization factor, multiplicity factor, Lorentz factor, absorption factor, and then the temperature factor. Okay. So polarization. So if we talk about the scatter, so if we talk about the structure factor, it is given by F. HKL is the summation of your scattering factor of a particular type of atom, Fn, and e to the power 2 pi I iota Hu plus Kv plus Lw, and for simple cubic, all reflection possibly present in all from all the planes. However, the reflection necessary absent from the none. However, for the body centered H, for the H plus K plus E1, then your reflection will be present, and then your H plus K plus L is odd, then your reflection necessarily absent. And for the face center H, K and L unmixed, that is all odd or all even. And for the H, K and L are mixed, then your reflection will be necessarily absent. And then this is your systematic absence. So permitted reflections. So for the simple cubic 100110111, 2002110, and these are if we see, all will be the present. These all are present. And for the BCC, your sum should be even. So 1 plus 1 is 2, and 2, and this is 4. So these will be present. And for the FCC, your sum should be HK and L unmixed. That is all odd or all even. So here all are odd, all are even, here all are even, all are even, all are odd. So these are will the present. Okay. So there are other factors also. So like the multiplicity factor. So this depicts that the relative position of your HKL planes contributing to the same reflection enters the intensity. Like for 110, all the planes like 111, 1 1 1 bar 1 1 bar 1 bar and 1 1 bar 1, and for 100 100 010 So the value of your multiplicity factor as a function of HKL and your crystal system. Okay, so the relative position of all these planes will contribute to the contribute in the same way as on enters the intensity equation as a Hartley P. Okay. Okay, so let's and also if you talk about the Lorentz factor, so this is based on the angular distribution, that is your difference in the delta theta, delta n by n, and then your geometry factor which affect the intensity. Okay, so there will be some set of planes which will be oriented exactly to the Bragg's angle diffraction, and then there will be set of planes which are slightly away from your Bragg's angle. So the major thing is this slightly away from your Bragg's angle will still contribute to the intensity. Okay. And then your Lorentz factor is given by 1 by 4 sine square theta cos theta, and then another factor was the absorption factor. So it is the number by which the calculated intensity is to multiply to allow for absorption. Okay, the material property. Another thing is the temperature factor. The temperature factor, as your temperature factor increases, the vibration of your atoms will increases, and then your interplanar distance and scale will vary. So this will also a significant effect on your intensity. And this is so the overall intensity can be written as your structural factor square times polarization factor P times Lorentz factor, which is 1 plus cos square 2 theta divided by sine square theta cos theta times absorption factor, then e to the power minus 2n. So and then the plane which is going to leave the atom, which is going to have the atom which have exactly half the wavelength out of the phase, will be somewhere inside deep of your crystal, right? And then there where the will be destructive interference will take place. Okay. So if meanwhile, if anyone has any doubt, please feel free to ask, write in the comment box. And then if we talk about scattering of an electron, scattering by an electron, then we can see that that the electric field which exerts a force on a charged particles, such as the electron, and the oscillating electric field of an X-ray beams. So these will set your electron into the oscillatory motion about its mean position. So the electron which has been set into oscillation by your X-ray beam, it will continuously accelerate and deaccelerate during its motion, and therefore will emit electromagnetic waves. Okay, and then these will have the coherence with your incident beam. Okay, so let's move to the problems. Which of the following statement is correct in the X-ray diffraction? So the intensity of the reflected wave increases in the angle of scattering. Increase is wrong. The elastic scattering of X-ray photons by an electron is called Compton scattering. Okay, C is the polarization factor is based, and because the incident beam is unpolarized, so C is the correct answer. So suppose we have characterized a crystallite material through XRD which has gone through two types of treatment. One is fully annealed and another is heavily cold work. What will be the effect on the X-ray peak broadening? So the cold work material will show higher peak broadening as compared to the annealed material because of the residual stresses. Okay, and then the third question is supposing an X-ray beam is scattered from a cubic crystal, which of the following set of planes will having the highest intensity in the forward direction? The answer will be 1 1 1, because 1 1 plane will be having the highest multiplicity factor. Okay, because if we see that 1 1 1, it will be 1 1 1 1 bar 1 1, then 1 1 bar 1 1 1 1 bar, the 1 bar 1. So therefore this will be the highest multiplicity factor. Which of the following sequence of peaks will appear for a disordered FCC material? Which of the following sequence of peaks will appear for a disordered FCC material? The correct answer will be 1 1 1 2 0 0 2 2 0 3 1 1. Okay, because the sum is even or odd. Okay, which of the following condition is true for X-ray diffraction of NaCl according to the structure? The answer is D, that the peak intensity at 0 for HKL having mixed indices, because it will be the subtraction of one Na and then Cl. So Then the solution, the structure factor NaCl is 4 times FNA plus FCl, where your HKl are all even. And similarly, so the F is your 4 times FNA minus FCl, and then where the HKl are all odd, and F is 0 where HKl are mixed. Okay. Compressive strain in the material will result the XRD peaks. Answer will be V, to shift at higher angles. Okay. Then the seventh one is that the structure factor of a crystallite material having atoms sitting at a coordinate 0, 0, 0 is, answer will be your A, F, because your uh, crystallite material having atoms sitting at 0, 0, 0, you can use directly the formula and then you will get this. And then given lambda is 1.5 angstrom, FW HM is 2 times 10 to the power minus 7, reading Bragg's angle is 60 degree. What is the average crystallite size of the material? So it can be, the Serre formula can be used at 0.9 times lambda by b cos theta, and theta is in radian, then you will get around 135. So if anyone has any doubts, feel free to discuss. Okay. Okay, then if no, then let's wrap up the class, and then you can mail me also regarding your doubts. Then we'll see you in the next week. So very good afternoon to everyone. So I'm Rohit Garat, and I will be taking the week 11's material characterization tutorial course. So the last day we talked about basics of a TAM, and from the TAM diffraction what can be inferred. So we were discussing about that in detail. So we discussed that phases and crystal structure types, crystal symmetry and space groups, orientation relationship between phases, determining growth direction, interface coherency, defects identification, example, twins, dislocations, ordering behavior of crystal structure and the site occupancy preferences. These are the things that can be determined from the TM diffraction. So like now the question was, why the electrons only? So anyone would like to answer that? So the ability to resolve the tiny objects improves as the wavelength reduces. We already know that from the week 1 class, week 1 lecture. So let us consider the microscope objective. Okay, so these are the objects to be resolved. So distance between the D, and then this is the focal length of the lens if image plane is at a large distance. And then so then we determined that the critical angle for resolution is given by 1.22 times lambda by D. So the minimum D for which we can still resolve two objects is AC times the focal length. Okay, so D minimum is approximately F alpha AC. Then it can be written as 1.22 lambda F by D. So a good microscope objective has F by D is around 2. So with lambda around 500 nanometers, the optical microscope has a resolution of around 1 micrometer. Okay. So let's continuing on that. So the resolution of the electron microscope. So firstly, we know that it behaves as light as well as matter. So behaving like light, it can be as h by lambda. Matter also it can be as. So and P is E by capital E by C. Then energy can be given as hc by lambda, and for if you consider it as a matter, then energy can be written as h square by 2m lambda square. So the for the wave behaviors, images and diffraction patterns, wavelength can be termed by energies. And for the charged particle behavior, strong electron specimen interaction, then the chemical analysis is possible. Okay. So like typically electron beam current in TEM is around 0.1 to 1 microampere, which corresponds to 10 to the power 12 electrons passing through the specimen plane. So with around 100 kilo electron volt energy, these electrons travel at about 0.5 C, approximately 1.6 times 10 to the power 8. So they are separated by 0.16 centimeter. This means that there is never more than one electron in the specimen at any one time. And further, the electron diffraction and interference occur, both of which are wave phenomena and imply interaction between the different electron beams. Now, for the fundamental constant and definition, we will talk more about the electrons. So, the charge is given by 1.6 times 10 to the power minus 19. 1 electron volt is around 1.602 times 10 to the minus 19 joule. So the rest mass is around 9.1 and 10 to the minus 31. Then the rest energy can be calculated, then followed by the kinetic energy. Planck's constant we know, then 1 ampere. So the speed of light in vacuum is around this. Okay, so the de Broglie wavelength of an electron can be given as lambda is h by p, and then the relation between the electron's wavelength and its kinetic energy E. So P and E are related through the classical formula, we know that. So E is given by P square by 2m, where Me is 9.11 times 10 to the minus 31 kg, and energy can be given as h square by 2m lambda square. So h is 4.14 times 10 to the power minus 15 electron volt second, and we can calculate E as 1.505 eV nanometer square by lambda square. So don't confuse this with for energy of photons, which is given by 1240 eV by lambda. And for electron, which is given by 1.505 eV nanometer square by lambda square. So let's solve an example. So we wish to observe a virus with a diameter of 20 nanometer, which is much too small to observe with an optical microscope. So calculate the voltage required to produce an electron de Broglie wavelength suitable for studying this virus with a resolution of d minimum around 2 nanometer. The F number for an electron microscope is quite large, so F by D is around 100. So try to solve this and we will discuss about. So we can solve it by d minimum is 1.22 times lambda F by D, and then we can so we find out that the lambda is around 0.0164 nanometer, and similarly we can we can calculate energy as 5.6 kilo electron volt. So that means to accelerate an electron to an energy of 5.6 kilo electron volt requires around 5.6 kilovolts. Now there is one more thing like I want to cover. So we discussed briefly about the SAED pattern in the last class. So we will discuss about indexing SAED patterns. So firstly we select the central spot. After selecting the central spot, we measure the distance between central spot and other nearest spots. This gives the so this gives the inverse of the d spacing 1 by d for a particular HKL. Now take the ratio of the distance measured. Compare the measured ratio with the expected from the table 1 given below. Now start giving the indexes for matching ratios as given in the table. Now cross-checking the indexing by measuring the angle between vectors joining the central spot and the other spots using the following equation. Now find the zone axis using any of the two indexed HKL, and then make sure that all the indexed HKL satisfy the zone law. Okay. So here I summarize for in table for all the details for you. So like these are the some examples, simplified examples for you. So pattern 1, pattern 2, pattern 3 and pattern 4, and then these other. So you can all try these and you can